Hey guys, so let me show you what this week's work has really been about. On this bench here we can see the old wire feeder of the Mi'kmaq welder that I'm working on, and well, we can have a look at the contacts here at these mounting posts. You can see 4 of them, and that is because this is a DC motor with field coils, a separately excited DC motor that works basically on the principles that also the washing machine motor worked on, that I have shown in a video a couple of weeks back. So this motor was originally powered by an old motor controller from the 1960s based on thyristors, or silicon controlled rectifiers, and that motor controller was in turn driven by an old mains transformer. Now the old motor controller didn't work anymore, and it was very complicated, and I really didn't want to spend 100 hours to figure out how to repair it. So I thought, why not just build a completely new power supply circuit that would not only take care of the motor speed control for the wire feeder, but also for other functions inside. Like, for example, there's a large fan inside the Mi'kmaq welder that cools the transformer, the power transformer and the rectifiers, and that is broken as well. So I thought, why not use one of these powerful 12-volt server fans here in order to cool the power transformer in the welding machine. So I built this circuit here, and it really took me all week to get this finished. And what this actually is a circuit that brings all these things together. Modern electronics, also this here, we'll talk about this in a second, the old transformers from the 60s, and the old motor. So these are basically 2 buck converters. The one on the left regulates the voltage across the commutator, so it kind of controls the motor speed, also independent of any load conditions, and that can be adjusted with this pot here that will go on the front panel. And then we have this other buck converter here, which creates a stabilized 12-volt rail from this transformer here, and that powers the server fan. Now we also have a bunch more voltages that come out here, like plus minus 15 volts DC stabilized, and that's for this thing here. It's a current transformer, or a current measuring transformer, manufactured by the German company VAC or VAC, and these are typically very expensive, about like 80 or 90 euros for one of these. But well, I was lucky and found one for $5 on eBay, and what this thing can do is to measure DC currents of up to 200 amps. That's why it says X200 here, and we can basically put one of the ground leads, for example, of the Mi'kmaq welding machine through here and measure the current, the actual welding current, without even making electrical contact to the electrical circuit itself, so contactless. The next thing is that I also have a 5-volt rail on here that I want to use to power a microcontroller that will also go on this board, I guess. And then we could later try to, for example, add another very powerful buck converter to the welding machine, and then we could have entire computer control over the power source, which is over here. The front panel is basically the only thing that has to be done now. 2 switches have to be added here, 2 rotary switches, in order to set the current the old-fashioned way. But I think I'm really pretty close to getting this running. So yeah, this is the next thing, taking care of the front panel and just installing inside what I have already finished here. This can then be done later on, but for now let me just demonstrate the motor controller for the wire feeder. So I'm turning on the isolation transformer, and there you can see that the power fan here is going on, and it's very powerful. You can see that it basically drags itself over the table, but we can just adjust the supply voltage that the buck converter gives, see? And just so that we don't have to hear it, let's crank it all the way down to like 2 volts or something. And now we could try to play around with the wire feeder itself. And in order to activate the wire feeder, these 2 wires are coming out of that, coming out of that enclosure, and that is what will go to the little switch in the welding gun. So when you want to weld, these contacts are closed, and then the motor over there starts spinning. Okay, and it's taken the wire that is normally on a spool that sits here. I've taken it out because it only makes things harder while I'm still working on this. But you have to imagine there's a spool of wire sitting here, and then it's just grabbed by that wheel and then transported to the welding gun. Now see, it's turning very slow. Now let's take away that and, you know, turn up this pot here. Now we reconnect the wires. It's a bit fiddly still. You can already hear it's faster. There you can see, turn much faster. And well, the thing that really happens here is you have a mains transformer, and then you have a rectification method, which is called full wave rectification with center tap. And that means that this transformer here has a center tap, that's the blue wire, and then you have like a symmetrical construction of the transformer. 2 24 volt secondaries and 2 32 volt secondaries. And then those go through each, through 2 diodes each, not 4 like in a full bridge configuration, but just 2 diodes. And then the center tap is just defined as the chassis ground. And that's just as good as full bridge rectification, only that you only have half the voltage of what you would get if you would just take the 2 24 volt taps and then connect them to a full bridge. Back in the day they often did this because then they only had to use 2 instead of 4 diodes. And in this case they actually were thyristors, and back in 1967 those thyristors would have been the most expensive components probably in all this. So what I have done is to charge these capacitors here over these diodes, and then we have a bunch of linear regulators here providing smaller auxiliary voltages, which then power these switch mode power supply controllers here, which then drive these integrated MOSFET driver bridges here, and they then switch 2 chunky MOSFETs on here. We also have Schottky diodes, and then we have like 2 large filter chokes that had to be individually calculated and wound and so on. Yeah, that's how that works. Might still be a little confusing for some of the viewers here, but I'll do my best to explain that in more detail and with some pictures and so on in the next video. Okay, so I hope that you find this kind of interesting and want to know more about this. See you soon.